Hello everyone. A beautiful saying says that happiness depends on ourselves. Moving further, in the last class we have seen the derived gates. So just recalling, in logic gates, first of all, what's a gate? Gate is an electronic circuit which has one or more input signals and which produces only one output signal. In logic gates, we have basic gates and we have derived gates. Which are the basic gates? NOT, and OR are the basic gates. Derived gates are NAND, NOR, XOR and XNOR. All these gates we have seen. Today we shall see one more topic, that is universal gate. Coming to the universal gates, last topic, universal gate. So what is a universal gate? Usually a question will be asked, what's a universal gate or which are the universal gates? Universal gate is a gate from which it is possible to derive the basic gates. The gate from which it is possible to derive basic gates. That type of gate is called as universal gate. Now, which are the universal gates? We have two universal gates. They are NAND and NOR. NAND and OR. These are the two universal gates. That means what? From these two gates, it is possible to get NOT gate, AND gate and OR gate. Now the question is, what will be the advantage of universal gate? If it is possible to have, if it is possible to derive the NOT gate, AND gate and OR gate, what will be the advantage of that? See, whenever we are designing something, designing the similar type of components will be easy for us, right? If you want to design a circuit, if that circuit is having a NOT gate, AND gate as well as OR gate, along with that other gates we have seen, derived gates also we have seen. By having the different types of components, the circuit will be, we will be having more circuit, or that means we will be having extra different types of circuits we will be having. So whenever we are thinking about any circuit, or whenever we are thinking about the components like mobile or TV, the thinner will be the better. Always we will prefer the thinner mobile, or we will prefer a thinner gadget. That's why if it is possible to have the NOT gate, AND gate and OR gate from the NAND gate itself, we need not have that separate NOT gate circuit, separate OR gate circuit, separate AND gate circuit. As we have discussed earlier, producing of the same type of gate will be easier as well as the economical, right? That's why we will be making use of this universal gate. That's the importance of the universal gate. Now we shall see how it will work. First we shall take a NAND gate. So what is the universal gate? Universal gate is a gate from which it is possible to derive the basic gates. It's a gate from which it is possible to derive basic gates. Important definition, it has been asked for the exam many times. Which are the universal gates? Again, 2 mark question. NAND and NOR are the universal gates. Now we shall take the NAND gate and we shall derive the basic gates. NAND gate we shall consider. First we shall take NAND to NOT, or deriving the NOT gate from NAND gate. We have seen how the NAND gate work. How does it work? What is the minimum criteria for the input? At least 2 inputs should be there, and NAND, otherwise it becomes AND. So the bubble of the NOT gate will be placed here, which makes it as NAND gate. If it is A, this is B, this will be A into B whole bar. That we know. That's about the NAND gate. What is our intention? Whatever value that we have fed should be complemented, but NOT gate works on only one input, isn't it? Whatever input that we have given will be complemented here. Now the question is, can we take A and B? NOT gate will be having only one input and only one output, isn't it? That's why now say this could be written as A NAND B, right? So now we shall modify this theme. Instead of having 2 inputs, of course NAND should have 2 input, but NOT can have only one input. What we shall do is, we shall take the input A here, and feed the same input. In place of A, of course it's A only. In place of B also, that will be A only. So how we have to write the expression now? Expression will be A NAND A. That's what A NAND A will be. A dot A complement. In place of B, we have A, isn't it? From the theorems we have seen in Boolean algebra, isn't it? So we know that if we have some expressions, we can have something like this: x plus x is equal to x, x into x is also x, isn't it? Idempotency law. So here what we will get? We will get A into A is equal to A only and bar. So what we have fed is A, what we got is A bar. So the output here will be A bar. So what we can say, whenever we are feeding the same input to a NAND gate, we are getting an output in the form of complement. It's complement. If you input A, we will get A bar. If you input B, we will get B bar. If you input X, we will get X bar. But here the same input has to be fed to the NAND gate, because the minimum criteria for the NAND about the input number of input is 2. More than 2 we can have, but at least 2 inputs we should have here. Okay, that's about NAND to NOT. How to get the NOT gate from the NAND gate. We shall move to the second one, that is AND. NAND to AND. Again NAND gate, 2 inputs, A and B. What we have here, that is A NAND B, that will be written as A and B complement. What we want AND, right? See, to the side we shall write, we want the result of the previous, that is NAND to NOT. What we have done there, we have taken the NAND gate, we have fed the same input If it is x, here we will get x bar. We know about that now because from the previous result, NAND to NOT. Okay. Now here when we have the output here, what will be the output? A dot B whole bar. What we want? We want NAND to AND, isn't it? That means if the input A and B are given, what should be the output? Output should be A. Since it is AND, we want it in the form of A dot B, isn't it? We want it in the form of A dot B. Now by looking at this, if x is there, we will get x bar, isn't it? Suppose we have inputted x bar, what we will get here? We will get x. What we have here? We have A dot B whole bar. What we have to get? We have to get A dot B. What we have is A dot B whole bar. What we want is A dot B. Again, we shall use the same technique, because if you are giving the input to same input to a NAND gate, we will get its complement. What we have is A dot B whole bar. What we want is A dot B. So input this to the second NAND gate here. One more NAND gate is there. Of course, in the first one we had only one NAND gate. In this we have two NAND gates. What we should do here? We have to get A dot B. Follow the technique. Input the same value, that is A dot B whole bar. How it will work now? Let us see. That is A dot B whole bar NAND A dot B whole bar, isn't it? A dot B, one of the input, this is x, NAND A dot B whole bar, that's y. One input you can take it as x, the other input you can take it as y, but both x and y will be the same because we are feeding the same. How it could be written? A dot B whole bar dot A dot B whole bar, and since it is NAND, complement. If this is x, this is y, we will write it as x dot y whole bar, but x is A dot B whole bar, isn't it? Again we have the result in general, x into x is equal to x from the Boolean theorem, idempotency law. So here also, if you consider it as x, the same value here also, right? If this is x, this is also x. In place of y, what we have is x itself, the same value, A dot B whole bar, A dot B whole bar. X into x is equal to x. So what happens here? If this is x, this is also x, because the same term. That's why, since x into x is equal to x, A dot B whole bar into A dot B whole bar is equal to A dot B whole bar itself, and write this complement. From the involution theorem, we know that x double bar is equal to x, right? So these two bars get cancelled. That's why what we get is A dot B. This is how we will derive the AND gate from the NAND gate. Hope this is clear. In the first place, from the first NAND gate, what we are going to get is A dot B whole bar. If we are going to input the values A and B, our intention is to get A dot B, that is A and B. We know that if the same input is given to a NAND gate, that will be complemented. So input this as the input to the second NAND gate, same input. What we are going to get will be A dot B. A dot B. This is one method. There is one more method which is somewhat complicated, even that we can try. See, this is the first method. The second method, here itself we shall write A NAND B, which could be written as A dot B whole bar, right? Which could be written as, from the De Morgan's theorem, what I am explaining now is the second method. Whichever method is easy for you, you can follow that. Which from the De Morgan's theorem, how we can write this? A bar plus B bar, right? In this case, which could be written as A bar plus B bar, this one, first input, NAND A bar plus B bar, which could be written as A bar plus B bar, NAND is later complement we have to draw, write the same, A bar plus B bar whole bar, isn't it? Again, simplifying the same, A bar plus B bar, De Morgan's theorem once again, bar plus A bar plus B bar, this particular bar, where we have divided it into two groups. When we are going to break that expression, this dot becomes plus, isn't it? Again, continue the same. Again, break this one, break down this. A bar, again bar, dot B double bar. Already this is plus, write that A bar, break this, bar dot B double bar. From the involution we know that A double bar is equal to A, B double bar is equal to B, which could be written as A dot B plus A dot B. We have this particular result, x plus x is equal to x, isn't it? If this is x, this is also x. A dot B, here also it's A dot B, which could be written as A dot B. Again we are going to get A dot B, which is AND gate, deriving the AND gate from NAND gate. So when we derive AND gate from the NAND gate, we have seen two methods. This is the second method. First method already we have seen. Whichever is easy for you, you follow that. Method 1 is easier compared to this one. Only thing here is we are going to implement this one using De Morgan's theorem, right? So AND gate as well as NOT gate we have derived. Now remaining is OR gate. Remaining is OR gate. Let us do that. NAND to OR. In this case, we will write it like this. First gate, NAND gate, that is A we shall have same input. Here we shall have in the same level one more NAND gate we shall have, feed the same input B. We know the result here. Whenever the same input is fed to a NAND gate, what we are going to get, isn't it? Because when we feed X as the same input to the NAND gate, what we are going to get will be X bar, isn't it? So for this one, for A NAND A, how we can write this? That is A dot A bar, which is A bar. So what we have here is A bar. Similarly for this one, B NAND B is equal to B dot B whole bar. B into B, X into X, that is X only, that's why B bar. So in the level 1, we have two NAND gates, A bar, A and B will be fed. The output of that will be A bar and B bar respectively. In the second level, one more NAND gate we shall have. Needs two inputs. We shall feed the output of the first two NAND gates to the NAND gate in the second level. So what will happen here? The inputs are now A bar NAND B bar, that is A bar dot B bar whole complement. A bar dot B bar whole complement. This is NAND and its complement. Now again we shall take the help of De Morgan's theorem, which says that X dot Y whole bar is equal to X bar plus Y bar. Follow the same. We shall go for that. A bar, break this bar, plus B bar. Again, involution law, which says that X double bar is equal to X. Complement of a complemented variable will be the variable itself. If you complement a variable two times, we are going to get the variable itself, which says that, which is equal to A double bar is equal to A plus B double bar is equal to B, that is A plus B. What we got now is A plus B plus for the OR. So when we feed A and B, what we are going to get here will be A plus B. Now we have seen, using NAND gate, we have derived the complement. When we have inputted the same input A to a NAND gate, we got A bar. Then when we inputted A and B to a NAND gate, we got A dot B whole bar, which is fed to the one more NAND gate. As the same input, we got A dot B. In the third one, we have taken two NAND gates. We fed A to one of the NAND gate, B to the one more NAND gate. Outputs we got as A bar and B bar. That was fed to one second level NAND gate as the inputs. We got the output as A plus B, that is OR gate. We got NAND gate, AND gate and OR gate. That's why, of course, NAND gate is a universal gate. Right? Similarly, we have to derive a NOT, OR and a NAND from the NOR gate in order to say that NOR gate is also a universal gate. We shall do that. Whenever we are proving this theorem or these results, we have to take the help of Boolean theorems, especially De Morgan's theorem, involution, as well as idempotency theorem. And now NOR to NOT. It is same as NAND to NOT. In place of NOR, in place of already we have seen about the NAND to NOT. Here NOR to NOT. In place of NAND, we have to draw the NOR gate. What happens? NOR gate. This is the NOR gate. Minimum number of inputs are 2. isn't it? If this is A, if this is B in general, what we are going to write is A plus B whole bar. This is about the NOR gate. Or this is OR, complement that will be NOR, isn't it? Now in this case we are following the same, that is we are following the same. There should be two inputs, but same input we shall feed, that is A. So what happens here? A NOR A. What's that? A plus, instead of B it is A whole bar. We have the result x plus x is equal to x. That's why A plus A is equal to A, and this bar is A bar. So what we get here is A bar. This result, this is just to understand, this is the drawing. For 3 marks usually they will ask derive and any of the two basic gates, derive and OR from NAND, derive NOT and from NOR, for 3 marks. So it's important question, deriving the basic gates from universal gates, for 3 marks. Hope this is clear for everyone, because the same diagram as we have seen in the previous NAND to NOT, only the difference is in place of NAND we are writing NOR. If there it was multiplication, this x into x is also x, x plus x is also x. That's why here plus A is also A, and write this complement, that's A bar. That's about NOR to NOT. Second one, NOR to what? See, this particular diagram, so for example we shall draw this one. In case of NAND, from this diagram we got OR. What we are going to get here? Same input we shall feed here. Let it be A, let it be B. So what we are going to get here? That is A NOR A, that is A plus A whole bar is equal to A bar. Similarly, B NOR B is equal to B plus B whole bar is equal to B bar. In the second level, we shall have one more NOR gate. Two inputs are required, minimum number. Let us feed the output of this to this one. What it will be? This is A bar NOR B bar, which could be written as A bar plus B bar whole bar. So which could be written as, by using De Morgan's theorem, what we can write? We can write it as A bar double bar dot B bar, one more bar, B double bar, because of the De Morgan's. When OR sum of two variables is inverted, it is equal to inverting the individual variables and ANDing them, isn't it? So A double bar is equal to A, B double bar is equal to B, so A dot B. When we use the same diagram, that is two NAND gates in the previous one, in the first level, and one NAND gate in the second level, we had A plus B. The diagram is the same, replacing NAND with NOR, but what we get is A dot B. So this is NOR to AND. In that case, when we use this particular type of diagram, replacing NOR with NAND, we had NAND to OR, isn't it? Remember that. So this will be A dot B. Now remaining is OR. Remaining is OR. We shall derive that. NOR to OR. Again, the diagram is the same as the previous one, just replacing NAND with NOR. So here in the first level, what we have? The first level, we have a NOR gate, input A and B. So what we can write? A NOR B, which is equal to A or B complement. So the output will be A plus B complement. Already in the first one of the results we have seen using NOR gate, whenever we are feeding the same input, A, we are going to get A bar. What we have to get is OR, right? What we have is OR which is complemented. So if we feed this as the input to the next NOR gate as the same input, then what we will get is A plus B, isn't it? That's why here also we need to do the same. So feed the same input to the next level OR gate, next level NOR gate. What we will have? A plus B whole bar NOR A plus B whole bar. This is the first input, this is X, this is Y, this is X, this is Y. But since they are the same, what we need to write is X and X. It is the same as this one. Again, we have the result X plus X is equal to X, which could be written as A plus B. This is X, and this bar we shall write. From the involution, we know that X double bar is equal to X. Complement of your complemented variable will be the variable itself. That's why we will get A plus B as the result, getting OR from NOR. So again, from the NOR gate also, we have seen how to derive the NOT, and OR. If it is possible to derive the basic gates from any gate, it's called as universal gate. So for both NAND and NOR, we have seen how to derive the NOT, OR and NAND. Once again, I would like to remind you that for 3 mark, deriving any 2 gates or even 3 gates may be asked. It's important for us. Whenever we are going to derive, write this symbol as well as the result. Just below that symbol you write this, then it will be clear. Don't just draw this figure only, write the expression also. Give the reasons wherever it is possible. That's all about the logic gates. Thank you.